loses in phase nearby, there's got to be resources to try to correct that, but there's big energy losses and other problems. And then non-linearities in the system become manifest. There are all sorts of issues, and we can't do everything. So you're gonna get a quick tutorial on the grid, and maybe my friend from Duke will actually give a presentation on insider's perspective. I'm hoping that Bob Moy, I mentioned, who's in the industry, will come and give it a high-level talk as well. But we're going to develop some crude models to get some insight in what happens to the dynamics of the grid, and we really need that to understand what we can get away with, what we can successful do in terms of. Well, I'll come back to this at the end. I mean, so there's all sorts of fantasies about the smart grid. Some of them are really cool, and some of them are completely stupid, in my opinion. And let's all try to work out which is which. And we have to understand something about the dynamics of the grid to even begin to address those questions. Okay. Oh, yeah, that's the pretty. I love that. And that was last week as well. That beautiful minus $400 in the south in New Orleans, and plus, I don't know, whatever, 400 in the north. Okay. God, I can't see a thing. Guess that's it. And okay, so I don't know. This is sort of a tutorial. This is all over the place, this lecture. I mean, I've got to give you an idea of what's to come. This is sort of like part 2 of the course, in a way. And also, there's a little bit of math that I'm going to force feed you. I'm sorry about that. Nothing as difficult as the convexity, but which you all suck at, by the way. Half of you, I mean, minimize 2x over x. Half of you are still saying the derivative with respect to x of 2x equals 0, which is 2, and if that were true, that would be awesome, but 2 is not 0. I don't have the homework solutions did that, and I wanted to strangle you, so yeah. The other half understood, so yeah.
Hopefully the other half.
Yeah, that's right. I mean, some of you just were intimidated by the computation. I can understand that, but I saw a lot of that, and it scares me. You can't do that on the midterm. You'll get a 0. So a quick recap in quotes. So first of all, I went over. I'm not going to recap this, but I went over another layer of the beautiful geometry and convex optimization, and the main message was the fact that you get these tangent lines over the graph of a concave function in general. Again, that's a definition of concavity. That is, at any point, the line above it, there's a tangent line. But the fact that you can actually compute the slope and see the concavity was something that you need to understand to develop algorithms. So that was the content. And in terms of what was missed, I'm not going to do it. I'll screw you. Can't believe it. Okay. I'm going to make you read this on your own, okay, for the midterm. It's no extra content, and I'll show you that. So, move it home. Oh, I see. I turned off the Wi-Fi. I guess it uses it. I didn't think it did. All this won't use it, I guess. Out of batteries? Oh, well, okay. Uh-oh. So, this one. Okay. So again, the problem is that we've got 500 generators in what's a BA? I mentioned this once. It's a balancing authority. Okay, so GRU is a tiny balancing authority. Florida Power and Light controls southern Florida and manages the grid. And a problem I mentioned is that Texas has 500 generators involved in the ERCOT ISO, which is Independent Systems Operator, which is a giant balancing authority, but maybe only 100 are online. And I mentioned that's a horrible combinatorial optimization problem. And you can, so this is just a few snippets out of what I thought I was going to present last time, which was crazy. It's too much. But one way people address these problems, and the way you formulate these mixed integer programs, is you introduce indicator variables. So if a unit I is on at time t, that's 1. And if it's off, that's time 0. So those are decision variables. You'd like to know if a generator is on or off. And you have to model, if you're going to extend the economic dispatch optimization ideas, you'll have to model the cost of turning on and turning off. So you'll have to come up with some abstract. I mean, of course, you're not going to get this exactly. It's an approximation, but you'll have some model of what's a startup cost and a shutdown cost, right? And then you get this new problem. Your cost function will just be modified. You're going to have the old cost function, at time t, if the unit's on and was on before, But if the unit was off and was turned on, you're going to have this startup cost you have to add on as well, And if the thing is off and been off for the last 2 units, it's gone. It's not in my system. And if I decided to go from on to off, there's a shutdown cost. That's it. So basically, instead of optimizing over the G's, now I optimize over all the G's, which depend on I and T, and all the U's, which depend on I and T. But note that this cost function doesn't have any coupling. This doesn't depend on Gj for another J. And so when you write down the optimization problem, everything goes through. You get a Lagrange decomposition, and the Lagrange decomposition is trivial because, even though you've just got I've got a time horizon of a day, and U takes on, it might be I'm looking at many times, but I know the structure. I'm going to turn the thing on for a while and then turn it off. So when I get a Lagrange decomposition, each of the individual problems is again trivial. You could just code it on your phone and solve this. Okay, so there's nothing hard about this at all. We don't have the same kind of algorithms because when we have discrete variables, we can't talk about derivatives. We can't look at steepest descent or ascent, whatever. But the Yahoo has a big warning because that is not a convex. We don't have a convex domain. It's not a convex function, and so there's no theory to support this. There could be a big duality gap. So what could easily happen is you go in and very easily solve this dual problem. And first of all, you find out that eta star, the thing, we try to minimize the sum of all these guys over all I and t. The actual optimal could be right there, so there's a gap. And there's a lambda star here which maximizes it, and lambda star is associated with some optimal G star and U star. So we're doing economic dispatch and unit commitment at the same time. We're because of the structure, but it's really unit commitment. All we care about is that, because we'll redo the whole thing with that. We'll redo it every hour. But it's possible this is meaningless. It's possible. But that's the beautiful thing is that many times it's not. Many times this gives you a reasonable answer. And it's a good starting point. Okay, so don't forget to fool around. Even though there's no theory to justify it, it often works. And so later in the course, I'll give you an example where this hacking really works. So the AC power flow problem, which has been an open problem in the power area forever, was basically cracked by playing games like this. Taking an incredibly non-convex problem, doing a Lagrangian relaxation just without even thinking. And through experiments, they found it worked. And it created so much excitement that now there's theory to explain why. And it's really, really awesome. But I don't think this worked that well. And so that's why when, I guess now it's Robert Bixby, so I sent you all an email, when his work was discovered by Dick O'Neill, so he's not all bad. So the chief economist at FERC is one who recognized the value of Robert Bixby's work on mixed integer programs, and it really changed the industry quite a bit. So anyway, so I want you to read these notes because it's a tiny extension of what we've done, and if you can't understand those notes, then you won't be able to do well in the midterm. So, you know, I'll think it over how I'm going to force you. So maybe I'll have some midterm question that checks to see if you read the notes. You know? Oh, I have an idea. I secretly put an error in there, something totally false, and I'll ask you what that error is. I didn't. Okay. All right. So reserves. All right. So we talked about reserves last time, and I'll explain what all this crap means as we go along. It's such a mess. All the things that we use to deal with volatility in the grid, you know. So I'll define replacement reserves, non-spinning reserves, spinning reserves, load following, blah, 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 blah. And a lot of the smart grid ideas are about how to supply these services, you know, because of the fact that there's more volatility and generators aren't happy doing it. Okay, so go to Wikipedia first, that's what I always recommend, and you'll see it's from FERC, you know, my buddies, FERC came up with this definition. You can read this, but it's really, all it says is anything but power. You know, anything that isn't energy is ancillary services. You know, and so I mentioned over there all these reserves. You know, scheduling and dispatch they call ancillary service. So that's sort of like our economic dispatch problem. And reactive power, so that what I showed you with the FNet plots, with the phase imbalance, trying to make that phase constant is part of controlling reactive power and voltage control. And there's loss issues, of course, in transmission lines, and how do you deal with that? And load following, of course, this is the ramping that's really fashionable right now, and in 5 years it might not be. So there's markets today for this, and who knows what will happen. And there's all sorts of security issues. I mean, system protection can be physical, and it can be cyber, and you know, energy balance. I don't know why that's differentiated. So anyway, we're going to talk about this a lot over the next lectures. And one of the best services, I mean, there are no good books here. I mean, our book isn't great, and there isn't a good book. But luckily, there's Brendan Kirby is a gem. And I'm going to force you to read some of his papers. They're really nice tutorials. So he gave a lecture last spring that I'll put online as well in a Florida workshop. But he's way ahead of the game. So Brendan Kirby was warning about the need for more ancillary services with renewables way back before other people were, and understands it better than anybody. So and he's a good writer. So he's the only source I have really for tutorials. There's no textbook I can recommend. Okay, so the first thing you have to understand is a lot of this has to do with volatility and uncertainty. But not the same thing, you know, right? That's volatile, you know, up, down, up, down. A sine wave is volatile, but you know a sine wave. You see the beginning of a sine wave, you can predict its behavior forever. All right? But volatility, so they're totally different things. So this is a histogram that you hopefully have seen before, and that is something that looks like a happy generation of a plant. I guess a pretty small one, like there's 200 megawatts there. And when that happens and why is a kind of uncertainty. Okay? So this is a kind of uncertainty. We don't know exactly what the load will be tomorrow, but based on past experience, we have a histogram. You know? And then this is a different kind of uncertainty. Things are going along beautifully, and wham, you know, there's an event. You know, and so uncertainty has no one definition. It's very hard to. There's no general, you know, way of talking about this. Okay, so historically, it's because of unexpected generator outages that we have reserves. You know, that a generator's going to go out, and you have to have somebody to quickly exchange and supply the missing power. Historically, that's it. In California, no way. In California, no way that's the motivation. They might say so, but forget it. They've got wild ramps in power that look like generators tripping one after another, and it's all because of solar penetration. You know? And then people like to say, well, then you shouldn't have had solar. Well, that's stupid, you know. It's really stupid. It's like somebody builds a car, and they don't know about shock absorbers. And the thing bumps around. Imagine a car without shock absorbers. It would bump around, and somebody said, well, we should have stuck with horses. You know, it's just idiotic, the arguments against solar, because we're having trouble now. We don't have shock absorbers. That's the problem. You know? And once we get shock absorbers, it'll be awesome. You know, and that's, I get excited when I say this because that's my thing. I mean, a lot of us in the room work on building shock absorbers for the grid. How to deal with smoothing that shock. Okay, and so here's uncertainty. I mean, we basically. That's, this is a bit old, but it's such a cool plot because that's 1 week in the Pacific Northwest. I've showed you this before. That's the other, right? And the green is the power output from the wind generators. And there's nothing. There was no wind that whole week. And then, wham, 2 nuclear power plants come on. Wham, 1 goes down. Wham, it comes back on. It's I mean, that's a lot of power. I mean, I know it's only 1/10 of Florida, 3 gigawatts. But Florida consumes a lot of power, okay? And so that is very smooth in a way, but the ramps are a big deal, and all sorts of features of this make this volatility a big issue to the grid, even if it was perfectly predictable. So even if I knew the shape of this for the entire year in advance, it would be, I think, just as big an issue. And I can think of an airplane. If you knew the torque hitting the plane through the whole flight in advance, do you think you would put all that information in the airplane? Suppose you knew microsecond by microsecond the torque on every little part of the airplane. Do you think you would put the terabyte of storage there to use that to fly the plane? You wouldn't. It's worthless. It's too much data. You're trying to control this thing in real time. So what we'd like, is it's nice to know there's going to be a ramp because we know we want to have the resources available, right? But this precise structure and all that detail we don't need, It's real-time control. It's really no harder, it's easier, I think, than flying an airplane. The control issues here, I think, are much easier than flying, than making an airplane fly. A lot of similarities. Okay. All right. And this is just showing basically. Okay, we're going to talk about this. These are balancing reserves. It's a term only used in this part of the U.S. And it's called regulation other places. But this is only meant to show that. So this is basically they tell the hydro generators ramp up, ramp down, ramp up, ramp down. So the hydro generators are asked to follow this. It gets a bit bigger during these windy days, but not that much bigger. But still, the ramps are what make the hydro generators angry today. The fact that this is steep slope. And so that's a different kind of volatility, right? What you're seeing here, compared to this low frequency volatility. And they're both important, and they're different issues. And if you think about airplanes, that kind of disturbance, that signal that's sent to generators, go up, go down, go up, go down. With the airplane analogy, it's like the ailerons going up and down. There's a real-time signal. The plane's trying to go solid. It flaps its wings in real time because it's measurements of its its orientation, all that, trying to keep it level. That's what that is. What was the analogy there with the airplane industry? The volatility you see here. What's similar to that in the airplane industry? Something that's there for. Oops. It's there for maybe a day and then gone.
Slower?
Yeah, I'd say exactly that's the best example. Basically, day ahead route planning. Oh, there's a Hurricane Joaquin coming. I better go around to the left. And here, oh, a lot of wind tomorrow. I won't need as much natural gas generation. So this would become a big part of the economic dispatch problem. And this again is the regulation that the flaps and the wings. Okay, so there's a definition from Kirby on regulation. So again, the flaps on the airplane. So online generation, responsive load and storage. So I mentioned the biggest battery in the world in San Diego. That battery will probably more than anything be used for regulation, the up and down, the flaps and the wings. So that managing the difference between actual and scheduled power flows in balancing areas, okay, and automatic generation control is sent out every 4 seconds to achieve this. All right. Now that is very skewed. So this is Brendan Kirby, who's thinking from the point of view of PJM, that's Pacific New Jersey, Maryland, in the Northeast, or California ISO, where everything's high frequency, like a few minutes up, a few minutes down, a few minutes up, a few minutes down. And the lower frequency part is all taken care of in an auction every 5 minutes, which is something I think is nuts, all right? Now, the Pacific Northwest, this includes all of that. This includes what PJM would do in the real-time market and what Brendan Kirby calls regulation. And so that's why it deserves a different name, because it's everything. Again, it's the real-time market in this part of the world, real-time market plus what Brendan Kirby calls regulation. Now, there's a lot of hype around PJM's Reg D signal. We're going to talk about this later on as well. This is a survey, okay? We'll get into detail on a lot of these issues. Which is high frequency, by the way. This is as high frequency as it gets for regulation. And you notice that's 10 minutes. So it's sent out every 4 seconds, but its frequency content is on the order of many minutes. It's not really high frequency. And that's as high frequency as it gets. And there's been big incentives to try to create markets for this product. Generators don't want to do that. Generators don't want to, that might be low frequency in our minds, but not for a big 400 megawatt generator. And so this is a good thing for battery storage, some other device like that. So because a few years ago, FERC came up with all these new market rules, everyone rushed in to try to supply this service. But it's not a big, in terms of magnitude, it's not a huge signal. So people got in early, made a lot of money on this. I doubt it's going to be the biggest thing. But we'll explain this, what Reg D is. And I understand a lot better now than I did a year ago. It's very complex, how they define this and how it's allocated. Okay, so these FERC orders, man, this is going to be fun over the next weeks. So FERC mandated that these ISOs pay for these services because there's zero energy. Reg D is designed to be zero energy, so it could be supplied by a battery. And they also made it very restrictive to keep a lot of players out of the game because they don't want it's costly. The FERC orders meant the price for this had to be very high. And so there's scores for precision, correlation, accuracy, and other metrics of performance. And so fast and accurate responses paid more. Mainly, you're not allowed in the game unless you can prove you can track this with some accuracy. The accuracy is only 25%. You can have 75%. You can actually, if you have a 25% error, you're still allowed in the game at PJM, which is wild. I don't know why they allow that. So again, this is that summary. This is a summary from Kirby, and I don't know if I want to go into this now, really, but yeah. But that's 2013, and then he would say this is all for contingencies, contingency, something you didn't expect. A generator goes out. And the spinning reserves are the ones that are online, spinning. They can just plug in. They don't have to, ramp up. they're online. They're at their G-min, but they're not actually supplying power to the grid. That's what's really crazy. They might not actually be hooked up. Yeah. You've got non-spinning reserves that are sitting there, and they can come on in an hour, say. What does he say? Well, he says 10 minutes, but it can go up to an hour. Yeah. And then replacement reserves, we're going to talk about this. So these could be very expensive generators. And so you don't want to keep them running. So they come in, and then these replacement reserves come on.
Where does the power go when they're not plugged in?
I don't understand this. I've asked this question to power engineers, and they don't know. Can you put it on the list? By the end of this semester, I want an answer to that. Yeah. A generator, well, Bob Moy would try, but I know that he when there are them, but the pump storage is in such a small part of the, that's what it should be, for sure. These guys are really, I would put these together. He distinguishes load following and regulation, but I'm going to argue over the next weeks that we should lump those together. Really, anything low frequency, we know we're going to take care of that through traditional generation that's going to be scheduled to go up and down. And then there's zero mean signals that can be taken care of at the highest frequency with capacitors, then maybe batteries, and then all sorts of other fun things that we'll talk about. All right. Okay, so there's an NREL glossary. I'm not going to go through all this, but this is just for your benefit, okay? So NREL, the National Reliability, wait a second. I can't believe I forgot the name of it. We'll forget it. I'll tell you. It's right there. We're NREL. National Reliability. Anyway, I'm sorry. I can't believe I can't remember the name. What the acronym is. Oh, National Renewable Energy Laboratory. That's right. Thank you. I got reliable and National Renewable Energy Laboratory. And you can see they have this huge list. And this is another thing that drives me nuts. They distinguish upward regulation and downward regulation. They distinguish between the flaps in the plane going up and the flaps in the plane going down. And it's an obsession with thinking about generators, I think. We want to fight that, okay? And AGC again stands for automatic generation control. We'll talk about that a lot. How generators are part of the shock absorbers, automatic control. All right, so I'll let you look at that. So that's a big survey of everything to come, and I want to go through, and we're going to need some models for what volatility is. I'm not going to expect you to know this in any depth. I'm not going to go and do what I did with the convex optimization, because you need 2 courses on this to understand it. But just some basic things so you don't make the same mistakes that everyone makes. We have to define our terms. What is volatility? What is randomness? So there's a histogram. Question, is that a volatile signal? So that's generation. So that's 160 megawatts of power. Is that volatile? Yeah. Well, we'll see. And how about that? Is that more volatile? Yeah. I'll tell you if I agree with you later. And how about that? Okay, so here's another question. Here's 4 plots. Oops, 1, 2, 3, 4. This histogram came from which of these plots? What? I heard that.
What is the x-axis represent?
What's that? Oh, yeah, so this is the deviation from the mean, okay? So 0 here, it's just there's a normalization here, okay? And so here, when you go to this, you can say, oh, the mean is 0, because we've seen a lot, So I heard one comment. So which of these corresponds to this? Okay, well, you're right. They all do. It turns out that this was designed so that every one of these signals has the same histogram, and it's Gaussian. I guess this is probably Gaussian with 0 mean and variance 1. All right. And so this is the most annoying mistakes people make when they talk about volatility. They think that that describes the problem, But, there's another one. Wow, I forgot about that. So those all have the same histogram. So volatility has to do with time as well as space. You've got the x-axis with generation, call that space, and you've got the time axis, and they're both important. Right? So I want to explain how you model this. So that's what the scribbles are, how you conceptualize volatility.
So the first one also?
Yep, I'll explain. I'll explain it. So I'll explain it, yeah. And I'll kill this. So how did I create those histograms? I mean, I won't tell you first how I did it, but I created data. And I use an X here instead of a G, because this could be anything. It could be, and I get a histogram. So I look at some interval of with delta, the area is proportional to the number of observations. And so MATLAB has a nice command for that. So if you type help hist, you'll get instructions on how to take a bunch of numbers and create a histogram. And the one I showed you was actually Gaussian. It wasn't. So how could I get this? I had an example where I showed you a plot versus time, and it was constant. Neil? Neil? Yeah. See? Somebody else? How could I get this? I showed you a plot that was completely constant. How could I get a histogram that looks like this? I showed you a plot for just one eye, Okay. Now this isn't a joke, because that's what happens in the Pacific Northwest. You'll show me an hour, it'll be constant. You'll show me another hour, it'll be constant. Show me another hour, it'll be constant. In time, it'll be pretty much constant, but it'll be a different constant every hour, roughly speaking. So it's just, it's crazy to think you understand volatility by looking at one trajectory. That's the thing. And so, So the way you model volatility is typically through a linear system. It's the most common thing that what you would do is you take something here which is normally assumed to be uncorrelated. And you're all supposed to have seen that before. I mean, it's supposed to be, your mommy was supposed to sing that to you, when you were a baby. I mean, definitely every engineering student should know what white noise is. Anyway, there's many definitions, but here's the one we'll take. Basically uncorrelated and a common variance. So you look at the mean of a random variable. You really, probability course is a prerequisite for engineers. I'm sorry, but anyway, if you look at the mean, it'll be either, it's got a finite variance. And uncorrelated just means that the cross this is also called the correlation, but the mean of WT times WS is 0. So this is just a model. You assume that there's white noise coming into some transfer function. H is a transfer function, and outcomes are X. And that's actually how I generated this. So in my example, what was it again? I took I took that, and so that if you remember your transfer functions, this is a linear system. I won't review signals and systems, but if you have a linear system like this, you've got a delay here. That's why you get a z to the minus 1. That's a one-step delay. It's a discrete time transfer function. I chose W to have to be white and Gaussian. So that N01 means a Gaussian random variable with mean 0 and variance 1. And in that you can use the MATLAB command. Okay, so in order to generate W1, W2, W3, W4, I just type in rand n over and over and over again. And I get that sequence. All right? So, what else did I have to do to get that plot? Well, I had to initialize, So basically I had to decide, how do I pick my x0, And so I chose x0 also to be distributed n01. So that means I have the right histogram at time 0. But I want to have the same histogram for all t. I want to be able to say everything's Gaussian. So for all of you, I wanted to be able to impress you with this, and I wanted to say that I'd always get a Gaussian distribution. And so there's two things to do, is that you go back and look at this model, and you look at, take t equals 0. You know, I've got x0 I defined to be Gaussian, and I'm adding on a Gaussian random variable which is independent of it. And when you add Gaussian random variables, you get a Gaussian random variable. It's another thing you should have learned. You know, you should. If not, it won't kill you, okay? You know, that won't be on the exam. But when you add Gaussian random variables, you get a Gaussian random variable if they're independent. Okay? And so, you could say this, well, so x1 is Gaussian, and I can do by induction, I'll find all the x's are Gaussian. So in order to make my dream come true, I just have to make sure the variance is right. You know? Because the mean's going to be 0. I mean, just take the mean of both sides. I mean, the mean of this is alpha times the mean of that, beta times the mean of that. That is mean 0. If that is mean 0, that'll have mean 0. So the mean is no problem. But how about the variance? So if I wanted the variance at this time, I'd have to take this and square it. All right. That, because this is 0 mean, that's the variance. And then I have to go through and expand this thing out. That's right. That's right. So you go through, expand this out. Oh yeah, thank you. All right. So you know, and the thing is that the mean of this random variable is the sum of the individual means. You know, and these guys are uncorrelated just by construction. All right. You know, because of the fact that I'm generating this white noise. That's the whole point of these models. That the new noise is not predictable from where I am now. And so that's why this ends up being like an alpha squared times sigma squared at time t. The mean of that is that. That's going to be 0. And this we already said was all right. So that to that. Yep. And the thing is, I want that to be 1. Right? And I want that to be 1. And I assume that to be 1. All right? And so it's going to be true that given this is 1, that'll be 1, provided alpha squared plus beta squared equals 1. And that's what I did.
Well, why did you not do alpha beta?
Oh, these are uncorrelated. You know, because W is in the future. You know, basically, I go back and look at the recursion again. xt plus 1 is a linear combination of past W's. You know, and so this is a linear combination of W1, W2, W3, and so forth, and x0, and that's one step in the future. So this is uncorrelated to everything that's here. Yeah.
So then we wouldn't be using the beta squared term because it's isolated?
No, I mean, right there. All I did was I squared it. You know, this squared, you know, to.
So the reason you didn't use the middle term was because
these guys are uncorrelated.
Right.
But W squared, it's the expectation of W squared is sigma squared W, which I took to be 1. All right, and T equals S. That's just WT squared. All right, and so you need alpha squared plus beta squared equals 1. All right. So if alpha, take a look at this. What happens if alpha is equal to 0.99999? You know, 0.5. I won't end it. There it is. I don't want to go on forever. I don't want to give the wrong impression. You know, beta is going to be really close to 0, right? Beta is going to be square root of 1 minus alpha squared. And actually, you can play around. We know about Taylor series. You could approximate this, but let's not. It's approximately equal to 0. All right. You know, so if you take alpha very, very close to 1, you're forced to take beta very close to 0 in order to make sure that's 1. And so the noise disappears, and you get basically a deterministic system. And that's why if you plot this, you're going to get, it'll look, I mean, eventually it's going to change. I mean, that's not 1, and that's not exactly 0. So this will drift along, you know. But you, in a short time period, you won't see it, you know. And so in the plot I showed where it was constant, I actually took alpha to be 1, and this to be 0. And you can imagine the other situation. I mean, if this is really small, then beta is really 1, then x and w are basically the same thing. And white noise, this means it can be everywhere. And so that's when you get temporal volatility. You know, just I can't draw it, you know, but you saw it, that crazy plot. So the most extreme temporal volatility that you saw was the case where beta was close to 1.
Now, can you call volatility is another term for signal attenuation? A lot of noise in the system.
Well, here I'm just trying to get the point. There's no one way to think about it, you know? I mean, you know, the thing is that, like, both of these are equally volatile in terms of histograms, you know? And both of them, when you think about what they mean in a power system, both of them are really bad, and for totally different reasons, you know? This is like I mentioned about the fact that you have 4 gigawatts of power one day and 0 the next. To deal with that isn't a big control challenge. It's an economic challenge, because you have to have resources available to be brought online to bring in that 4 gigawatts of power that's not there. You know? And over here, that high frequency stuff that we saw over there, that's, you know, that ramping there puts, you know, means there's a lot of wear and tear on generators and problems. So it's just, I'm just trying to, you know, pound into your heads that volatility and randomness are very, very subtle issues. In a histogram, somebody shows you a histogram, just laugh at them. It's meaningless. You know, there's just way too little information in a histogram. You know, and so this transfer function modeling has a lot of information. You get a lot of insight. You know, you can, once you know, have a linear model like I showed you, you can tell what kind of volatility is and how you would address it. You know, that's all I wanted to say there. All right, it's one class of models. All right? And it's popular too because you can simulate in MATLAB like that. I want to keep that. Kill it? Yeah.
Can you explain what the two graphs are like that?
Well, again, look at the, you know, look at how the successive values evolve. You know, if alpha is close to 1, we said that beta is close to 0, so it's just like it stands still. And that's all I'm showing here, you know. And this is just the opposite. So this is the case where this is practically gone, and beta is 1. And if you actually try to plot white noise, you can't really do it. It's just, you know, just a scatter plot, you know. and maybe that last plot I showed you was, I don't remember now, but it was, I think it was beta very close to 1.
What is white noise specific?
Well, that's the definition. Well, it's erased now. The definition is uncorrelated, as I showed you. What I showed you. You know, so we have some random variable, take the product, and you find it's 0. If t is not equal to s, it's a very weak notion of unpredictability. Very weak sort of. That's the conceptually. Is that if I observe all the w's up till now, it's kind of hard to predict the future. Very weakly though. I mean.
S is like my domain.
What?
S is supposed to be the.
Oh no, these are just 2 times. That's all. No,
Which is 0 and 1 and here.
t could be 12 and s could be 80. They're just 2 different time values. That's all.
But S is like an open range.
No. These are both times. I mean, if that's confusing, just write T1 and T2. Okay. So the definition of white noise is if I take the mean, you know, the correlation at different times, I'll get 0. That's all. All right. So it's not. Oh yeah. No S. I'm not gonna. Well, we'll see. All right. So I remember this. What's up?
So white noise just represents uncertainty.
Well, it's a building block of models. So basically, how can I fit like what I see in the Bonneville Power Authority? How can I create a model of those observations? One approach is to hypothesize that it can be approximated by a linear system driven by white noise. And that's the most standard way of trying to fit data. And you do this. You do this partly because you want to write code and try out experiments. You know, you don't want to just take traces of data from Bonneville Power Authority. You want to be able to create a simulator for doing experiments. Yeah.
But here I'm also assuming that t plus 1 equals t, right?
No. I mean, take a look. This is just evolution of a. This is how I showed you those plots, you know, of generation. It was G there, now it's X. And this is how I did it. When I wanted the next X value, a G value, I took, you know, a shrunk down version of the previous value, and a constant times WT plus 1 was obtained using MATLAB, RAND. This is just a for loop. Yeah, so that's all. Yeah. All right. You don't like this? All right. Anyway, so that's one way of thinking about things. So, So I said one was okay. That's the most standard model you'll see, you know, anywhere around, and you get some insight. I'd say mainly it's useful for coding, but this transfer function H tells you where the frequency lies. Like does this signal have a lot of high frequency components or low frequency components? Which was kind of the thing I was getting in those plots, right? The first plot, mainly low frequency, constant trajectories, and later ones had a lot of high frequency content. That was approach one. Approach two is just go directly and forget white noise. Just express X as a sum of sinusoids. And this is kind of crazy, and I'm not going to spend a lot of time. This is an entire course. And I want to torture with this for just a little bit. So I won't do this for very long, but so I'm taking complex exponentials, and maybe I shouldn't do that. Maybe I should just go straight to sines and cosines. But if you all claim you know about, remember phasors, you remember the complex exponential is. And I'm going from minus n to n because in order for this to be a real signal, we have to put some assumptions on g, and the g's will be complex conjugates. So that star does not denote optimization, but the complex conjugate. So if I look at g of minus k, that's gk complex conjugate. And if k equals 0, it's real, because 0 and minus 0 are the same. And you could go through and work this out. At t equals 0, or k equals 0, we just get g0. And if we go through and say, well, I know it's real, just take the real part of both sides, you know. And what you're going to get, if you do that, all right, so if you just express the complex exponential as a cosine and a sine, j times a sine, take the real side of both sides, you get a 2 because the negative terms and the positive terms are the same. All right. Now, this, of course, is conceptual because you can see it. And but these are random. But the gk and theta k, in MATLAB, you'd use some rand command to get them. They're random. You know, and this is not a stochastic process course, so I'm not going to define what I mean by that. But if you went to simulate this, you would generate gk and theta k from some distribution. Maybe theta k could be uniform and gk could be uniform, or something like that. You know. And then run this. But the wild thing is that you only do it once. So you generate these g's and these thetas once, and then you let this run forever. Amazing fact, there's no difference between the two models. You know? So any system of this form can be written, at least, I mean, you have to let n go to infinity. But anything that can be expressed in this way has a representation in this way, and vice versa. You know, so it's a nice conceptualization. Yeah, isn't that wild? You know, that a random, this thing that I talked about just now, this linear system, has another representation. So here you've got shocks of noise entering the system. It's physical. A gust of wind, something hitting the airplane. You know, this is physical. These guys have no physical meaning whatsoever. It's just conceptual value. And you can compute G based on H and everything like that. And so random, you know, basically all the randomness can be thought of as happening once, and then things move forward. All right. Yeah. Probably. Yeah. Thank you. So it's a conceptualization that's really useful because we've got these disturbances, and we can say, well, the high frequency guys, but we'll see this, the batteries can take care of those. And hey, look, there's not a very high content there. We don't need many batteries, you know? And this mid-frequency part, well, we'll need generators for that, or we're going to use demand response or something like that. And so being able to conceptualize a disturbance is just a linear combination of sinusoids is useful concept, all right? So take stochastic methods 1 and 2. Yeah. All right, I'm done with this. I guess a couple of you are in there now. So this is all the linear theory in 1, and more nonlinear theory in 2, right? So, but anyway, that's the take-home message. There's 2 ways of volatility and randomness are hard to define, and these 2 models are probably the most important conceptual models here. All right. So where are we? I bet it's time for a break. 3 o'clock, yes. What the hell? Wait. 3 o'clock, really? Okay, let's take a 5-minute break, and we'll play around with this a little bit, okay? And just a few more words on this.
Do you have our homework by any chance?
Oh, well, that's the thing. I have it. Thank you for reminding me. I've got homework 1 and 2 with me. Tried it out. I've never simulated this, so which is I'm surprised I've never tried. But who cares? So I want to blow off contingency reserves, my least favorite topic. We will come back to it because, when you understand contingency reserves, it does help to think about these huge ramps that are, a big issue today. But why is it that California keeps that huge amount of extra power available, and they go into panic mode when that gets small, and Texas raises the real-time price to $9,000 a megawatt hour when that gets small? Why? Because Texans are crazy. I think that's I mean, I don't. What?
What the reason was why they raised the price cap?
Because of the naive economics that I all showed you. That the price should go up to it should go to the marginal value. And it's not politically feasible to wait for negative reserves to do that. So they do it in advance. It's completely wacko. It's the naive economics I taught you all. It's completely crazy. And they're the most extreme, right, in the United States. So it's like a $3,000 cap in the rest of the U.S., which I think is too high too. I don't know I don't get it. I mean, I don't see any value.
So why did they remove the price cap? What was it?
Well, the thing is that right now there's a problem of incentives, and they think they'll fix it through allowing the prices to go high. And the economic theory I presented to all of you supports that. Because, if I put a price cap in my model, all that theory would disappear. The average price would no longer be the average marginal cost, because there was a unique equilibrium, and it was either the price was marginal value or marginal cost. And economists know this, and that's why they say, you're messing with our theory by having price cap. Our theory doesn't work, so get rid of the price caps. That's really, it's just, so it's amazing to me. All right, so we're going to look at so I told you models for the, recurrent, steady variability, like wind over a month, or higher frequency volatility in ramps from wind. This is about black swans. So the story of black swans? So statistics, a lot of statistics is not a boring science. The real statistics is actually quite beautiful, and a lot of it was developed in the UK. And in the United Kingdom, there was no such thing as a black swan. And it was actually used as a joke of what's the probability of a black swan? Well, it's 0, they don't exist. And little do they know that when they exploit in Australia, they find out black swans are everywhere. So given their model of reality, the probability of a black swan was 0, but they hadn't been to Australia yet. So there's a lot of history on that, on the word black swan. So when somebody says black swan, that means this absurdly can't happen, and they're common. It's just that they weren't observed yet. And that's the thing about all sorts of risk. I mean, I can't resist. I mean, nuclear power is so sweet. You know, uranium is free, and you know, and we are really good at handling uncertainty and risk, right? I mean, airplanes are amazingly reliable. But we've never seen what happens yet. I mean, the black swan of a nuclear power plant really going out. You know, when we see it, we might change our model of reality. You know, so I love nuclear power, and I hate nuclear power. It scares me to death because I haven't seen the black swans yet. You know, and when people talk about the probability of a generator going out, they're nuts. You can't model these things. Just like you know, can we model the probability of a black swan in Australia? I mean, now we can. We've seen them, but before you see it, you can't model it. And the same thing is true of nuclear power. It's really hard. Even though I think it's better than a lot of things. So here's some metrics for contingency reserves, which really are like these black swans, because these things don't happen. We don't have a gigawatt of power dropping out all at once unexpectedly, you know. So when they talk about loss of load probability of not having that power, so the load, you know, that many gigawatts of power disappears on the supply side, or the load jumps up 2 gigawatts on the supply side, on the demand side. You know, that doesn't happen. You know, so when they talk about the probability of lost load, of not serving load, they're talking about something where you don't have observations of this. You know, and so they have numbers. It's 0.0000864, or 1 blackout every 10 years. But it's a joke, okay? There's no way you can verify the models, you know? You can't do repeat experiments of the Earth over 10 years. It's just, you know. So anyway, but it is used, and you'll find in every book, including this textbook, and it's used seriously, even though it's not quantifiable. There's the value of lost load, which we've been looking at. Wait, D. So remember, minus $20,000 slope. That's the value of lost load. You know, so D0 is the nominal demand. You know, and if I have to shed so many megawatt hours of energy, I'll have to pay $20,000 times that. You know, in restitution or something, you know, something like that. And so,
20,000 for a reason.
no, I made that number up. Remember, whenever I use $20,000, it's just our made-up number. And so, the value of lost load is deemed to be $3,500 per megawatt hour in one order, you know, 2009. But then. Now, I mean, ERCOT wants to be $9,000 basically. That's what they're sort of saying with their $9,000. Yeah, the value of power. If you lose a megawatt hour of power, how much does it cost Texas society? I mean, please laugh with me. I mean, you know, I mean, can you imagine if the poor houses have to be a degree warmer? That's all it would mean. You know, to lose a gigawatt of power was nothing. You know, in terms of the energy that's wasted and. Look around. But anyway, they come up with formulas for what is the value of power, you know, and I don't know. All right, and then there's the expected energy not supplied, which is related to this loss of load probability. I'll define it. Okay, so those are 2 metrics, and that's just a number that they stick in. So, I say that both of these are arbitrary things. I mean, the value of lost load is undefinable. You know, it depends on who you're shutting off. You know, nobody would mind if I turned off the lights. You know, and but they'd mind a lot if you turn off the power at Shands. So it's totally has to do with geography and everything. And this is something nobody will ever be able to say they've computed it. It doesn't mean anything. But it is absolutely standard practice to pretend you know what these are and then make calculations on it. And that's all you can do. You know, if you've never seen a black swan, you just come up with some, everyone shares the same assumptions and admits that they're crazy, and they come up with conclusions. So that's life. But so the black swan model. So you assume you have a time period of interest, say 5 years. And you have a model of every scenario and its likelihood. So this generator trips, causing this generator to trip, and the world ends. Or, you know, this transmission line goes down, and that causes a cascading failure. And they have supercomputers for this, you know. And then they make a histogram. You know, so basically, for a given mean value of power available tomorrow, you know, you look at a trillion scenarios of different kind of problems, and then based on that histogram, you look there, and that's the probability of blackout. That's the loss of load probability. Yeah, and you know, you can see my smile, right? You know, they want that to be really small. They basically want it to never happen, right? And so, trying to estimate a distribution, the very, very tip of the tail, you're not going to do it, you know, because you won't see this. You'll never see it. All right.
Did you say that the x-axis was?
So, oh yeah, oh sorry. So this is this is generation, okay? And remember, this is a histogram. So I did all these experiments. I got my supercomputer running and looking at every bad thing that could happen, you know. And you know, generators going out, or you know, or big ramp of wind, or you know, all sorts of different things. And remember how to find a histogram. So if I look at an interval, the area of that curve is proportional to how many observations I've seen. You know, but the area of the entire thing is 1. You normalize it to 1. Yeah.
So like the height.
The height. Well, it's a probability density. It would be, without normalization, if I look at an interval, the height is the number of times I observed generation being in this interval.
I thought the width was the width.
No, the area. Yeah, the width is the, you know, and so this could not be just generation. It could be generation minus, well, it could be, it could be the scheduled generation plus wind plus solar and all of that. You know, and so it also includes blackouts, includes the dynamics of the grid, includes the fact the generator goes out at 6 a.m. There'll be, you know, all these services to bring stuff back online. So all the control is part of this experiment, and then you want to go and work out this probability. So So that's why. So this just explain. This is what's done. You know, you don't get a number that really makes sense, but what happens is you'll have a loss of load probability target, and again it might be 10 to the minus 5. And the mean here is something I get to choose. I can choose how many generators are on, and so I can move this to make the loss of load probability smaller. All right, and so that's it. So here I've just converted this to math. I said it's the area under here, which is a loss of load probability, you know, which is an integral of the density from minus infinity to d0. So I've just smoothed out the histogram. I fitted it to a Gaussian density in this case, you know, and I've got to perform this integral and make that equal to the target. And I'll do that through design. I'll do it through scheduling. That's how I'll choose how many extra generators will be online for the next day. Okay, and I really just do this once, you know, once a year, or once a new FERC order is passed. You know, I'll go in and figure out what, you know, how much extra generation I need.
So what's R bar prime? R bar?
Yeah, I'll explain that as we go along. Yeah, yeah. Or maybe I won't. I just realized this is from another talk. I should. It's a mistake, actually. Again, this is the area. That is the area under this curve here. All right. Okay, so, you know, so this, you know, That's how you get 12% reserves in California, or in some places. You get it because they played some tricks like this. But in the end, 12%. It's a nice number. Yeah, at least, yeah. And where are we? So now we get to me doing the homework for you. Yeah, we can do it. Now we get to something that could really lead to something a bit more useful. So when they talk about the expected energy not served, they do typically assume a function like I've showed here, where you have the negative slope there is the slope there's a minus value of lost load, just like I wrote there. And this, is sort of arbitrary, but there's some cost having extra generation. There really is. I mean, you've got to pay somebody to be around, And there is a cost because if it's spinning, it takes fuel, and there's a pollution cost. So there is something roughly linear over here. What I would really fight against is that. Okay, this is what's done in practice, but the big mistake is assuming that linear structure. So if you really thought about it a lot, a much more reasonable model would eventually maybe get that steep, because that's when Shands Hospital is being shut down, But that, again, is turning down the lights in this room, and that is sending the undergraduates home for the day and shutting down the undergraduate classrooms. And actually, I used to joke this was shutting down the elementary schools, but I forgot about parents. Shutting down elementary schools would be over here. The parents will, they'll kill somebody, maybe, But really, it would be a very elegant convex function. And if people recognized, well, there is flexibility from loads, which there is, then you could take advantage of that. And then actually all this would make a lot more sense. Because when this isn't so steep, we're not looking at the tails anymore, and our answers are much more realistic. Okay,
But you can't, what's it called, find a
you can.
equation of that
Well,
line, could you?
that's a contract with the University of Florida. But they will shut down so many kilowatts. We'll give you so much money per year if you let us shut down so many times per year. Yeah. Well,
Is that like a thing that happens?
that's the thing that's happening. It's starting to happen. So I'm jumping ahead of myself. And maybe I should. I don't know. You should do this in the homework yourself. But FERC order 745. I've got to stop now. Now that you said that. So I mentioned this in the beginning of the course. So this was struck down in the middle of the semester last year while I was teaching this course. And it was exactly an order from FERC to mandate payments to loads to shut down, based on some sort of market scheme. And it was shut down. It's gone. So it was killed last year. And it's at the Supreme Court this month, October. It's very exciting to me. And I mean, it's how they rule on this is going to make some people a lot of money or go out of business, and it's going to have incredible impact on the grid. So this is done. Alcoa has contracts with PJM to shut down. Every day they'll shut down. So if something's going on, they'll ramp down. I mentioned Florida. The Florida On-Call program will shut down pools, but not very much. But it could be done a lot more, and it would make much more sense, because that has nothing to do with reality, that straight line. Nothing to do at all. Pretending that the value of Shands Hospital is the same as the value of the lights in this room, it's crazy. All right, but it leads to nice math. People like answers. I think that's the main thing. You know, somebody comes and says, "How did you get that answer?" You say, "Well, I did this." you know. So basically, you have a target for how expensive is my plan, you know, and you go and do this integration, and you choose your extra generation, spinning reserves, and all of that, so that your cost meets the target, you know, there's that. But let's see. Yeah. I'm going to spend a bit more time on this. Yep. Yeah. So this is how you define expectation in probability course. You say P is a Gaussian distribution. Say, you know, and C is my cost function. The mean. This is the mean. You know. So that's symbol E that I used before. It's just the mean of a random variable. So say G here is the distribution generated tomorrow. I haven't seen it yet. It could take on a wide range of values. A Gaussian assumption is probably pretty silly. You know, and it's probably very strange distribution if we looked at a histogram. But whatever it is, once we get a histogram, we can fit it to a density, integrate, and try to match this target, and actually try to do some optimization. And yeah.
How would, if that was the slope, then what would be the...
It'd be the same thing. There's no difference. Whatever, this formula is the same. Yeah.
I know, what would you choose VOLF?
Oh, it depends on my contracts with consumers, you know. And basically, just like we came up with these marginal cost curves, this is marginal value curves. You know, so the marginal value at Shands, I'll bet it's a lot more than $20,000 a megawatt hour. You know, and the marginal value, again, I don't know, all of UF is nothing compared to Shands. I mean, So it would be maybe you'd have auctions, or something, But auctions once a year for contracts not when you're in the middle of a crisis.
So wait, at that point, would you still integrate from infinity?
Yes, it's a completely different setup because we're not looking at the probability of disaster, which is really crude. Here we're trying to look at the cost. How much will I have to pay? And you're trying to maybe minimize that total cost, that mean cost, or just try to reach some target. And this is still weak because the mean ignores a lot of risk. It's the variance of this should be taken into account as well. How much, if my, I don't know. I mean, Anyway, that's something that's another topic. But when you have something that's very flat like this, the mean doesn't scare me as much. When you have something very steep, the mean scares me more. The fact that I think not looking at the spread around the mean, it seems a mistake. Yeah. All right. So actually, I do have my R bar here. And a second. Didn't I have it here? It seems like I dropped a. Anyway, so I'm going to put a bar here. So I've got that nominal demand here, say, which I've this is just sort of the mean for the demand expected the next day. And I'm going to have some G bar here, which is my scheduled generation. And the R bar you saw is the difference, is the reserves. That's that 12% that we see in the California ISO or other places. And that's really the thing we want to optimize then. You know, basically we schedule so much, and of course it'll depend on the mix, you know, but we'll take that into account as well. But basically, bring it down to a scalar quantity. How much extra power do I want, you know, relative to my nominal demand? You know, and then you can take that as a variable of optimization, and you can actually go and plot this, and so you can change this around. And so let's see if I can do this. So what have I done here? I have this density, which of course depends on how much reserves I chose. You know, this was the amount of resources I have the next day, and that histogram. If I don't schedule anything, it's going to be nothing. You know, but I'm going to schedule something, and the more if I schedule more, that density will move. Now, that's a kind of abstract assumption to say it just moves linearly to the right. You know, that the more reserves, the more that density moves along. You know, but because you know, if you ask for a lot more stuff, they might be very bad generators then. So when I ask for more reserves, I'm asking for really unreliable generators to go along. This density might actually become, with more reserves, get flatter, get more variability. But it's a good approximation for starters to say that if I have more generation, I just move the histogram. You know? And then this changes. Where'd it go? Yeah. So we can go through it. So again, this is a yeah, that's right. I've got a cost function. It's minimized here at d0, and the cost is from deviation. If this is positive, I've got extra power. If it's negative, I'm having to shed load. And by doing this, you'll see I'll get a nice convolution formula, sort of. And there it is. And I can choose this to match a target, or I can just minimize it. You know, just basically just take derivatives and set the derivative equal to 0. And we all know about convolutions. It's sort of, that's a bit annoying, but it's like the integral of something times g and p0 g minus r. It's not quite a convolution because this should be flipped around and stuff, but you can play the same games and you'll get that. So I can move this over here. And do you know what the value of that is, of bringing the r from here to here? It's easily the same thing.
The value is?
Why, in terms of analysis, thinking about this problem? Have I got it here? So what I asked you guys to do in the homework is you all can feel right now, having stuff fed to you sort of fade out after a while. This integral here, I'm asking you to plot it. You know, that expectation of C not the bar. So again, this shows you how that expected cost depends on how much reserves I've added, you know. And if you plot it as a function of R bar now, you're going to find it's a beautiful convex function. So I'm going to make you do that. So in the homework, all right. And why is that? Well, you know, an integral is like a sum, right? Now, if I look at a particular fixed g, you know, and d0 is fixed, okay? This is just our, you know, it's a piecewise linear function of R bar, which is convex, you know. And basically what I'm doing is I'm just looking at, I'm shifting, when I take different values of g, I'm taking a bunch of convex functions and I'm adding them together, taking a linear combination. And an integral is just a limit of taking sums. You know? When you take a convex combination of convex functions, you get a convex function. So this is going to be a convex function. And from here, if P0 is Gaussian or a nice density, you can kind of imagine this very smooth function of R bar. Right? You know, this is a Gaussian density. It's really, really smooth. So you move R bar, you don't change things much. Here, this is not smooth. It's piecewise linear. But this is useful for computation. This is useful to know it's smooth. And this is useful for computation. And also say, hey, it's got to be convex. You know? And so it's convex. It's going to have a minimum. In this case, it's going to be unique. And we can compute it. You know? And so it's actually, it makes it quite nice. We can think about the sensitivity. And remarkably, the sensitivity of the optimal value it's not that sensitive to the cost. It's really surprising if you have under certain conditions. I feel like I have to stop. Yeah.
You always want to minimize R bar, right?
Well, we want to minimize this expected cost, you know, and that's going to depend on how much extra reserves I have in place. You know, and so I started out saying it was a target to meet. That might be more realistic in a really complex setting. Let's say we want the expected cost to be below some threshold. In a simple model like this, we can compute it. We can get a formula for this. It's,
So you want those reserves to minimize the cost.
yeah. That's what you do when you look at this expected energy not served. Yeah. Oh, there's a little bit, you know, I mean here, expected energy not served typically ignores this over here, but, you know, I mean, the reason there's a target is often they set this equal to 0. Anyway, so I'm not going to do it. I'll do this next time. The calculations, we're not up to calculations right now.
It's not minimized, right? Let's say
Yeah.
C cost.
No, there's one.
Target cost.
So either we can. So there's two things we can do. So again, typically in the industry, you do have a target. You know, and the reason they have a target again is they often ignore this part of the cost. You know, and if you ignore this part of the cost, your minimum is going to end up sending the reserves equal to infinity. And so instead, they have a target. You know. But given the fact that we know this cost to reserves, it's crazy not to include that. And anyone in industry would agree with me. You know. And so alternative to a target is to just minimize. And I don't want to do it now. I feel like it's too late in the day for that. Yeah. So you're going to start, I'm not actually making you do this, but you're going to start this in the homework, and then we'll finish up next time. And so the schedule really is, I'm not going to say much more about probability. I will expect you to understand this stuff to this degree, you know. The upcoming weeks are going to really be about grid models, you know, swing equations, and because we need to understand the dynamics of the grid before we even talk about ancillary services and how we're going to do it. We have to understand the system we're trying to control before we start talking about control solutions. Okay, so that's why we'll get into the textbook and all these swing equations and droop gains and all of that before we come back to ancillary services. Yeah. But yeah. So anyway, we'll do it next time. All right, homework. That's right. One of these is homework 1 and homework 1 is homework 2. I just kept them separately here. I will not be here on Tuesday. In fact, part of the reason I'm a little nervous at this moment is I'm about to run out of this room.